Okay, we're going to look at intermolecular forces, which is the last part where we're going to be dealing with the attraction between molecules. Well, the first thing we're going to look at is a term, and that's actually an intramolecular. Okay, intra means inside or in between, but inside my molecule. Okay, so this is the force or the bond, okay, that is inside a molecule between two atoms. So for example, it would be like the connection between a C and an H. Okay, this right here is an intramolecular force. It's the bond between two atoms. That's an actual covalent bond, okay, between two atoms. That's intra. Okay, these are usually fairly strong. What we're going to actually look at is that these are actually stronger than the force we're going to look at here in a second, which is the intermolecular force. And usually I do intermolecular force as IMF, which is what we're going to look at here in a minute. Okay, so we're going to look at now the weaker of these two forces, because technically the one up here is not really usually a force, it's actually using a bond. Okay, but intermolecular forces, again, are the force now between two molecules. You're going to look at the word and think about it as inter, like an interstate. Okay, interstates run between states. An intermolecular force runs between molecules, intermolecule. These are the kind of forces that keep things together. So there's a reason why we don't have just one molecule of something. Okay, why we can see things, why we have a whole glass of water, there are tons of water molecules. All those molecules are stuck together. If they weren't all stuck together, you'd have little bitty atoms everywhere that would be separate. Here they all kind of stick together and make one big solution or one big liquid or solid or gas or whatever that we can actually see. All right, they tend to vary in strength, and they vary in strength based on what your positive or negative attraction is. If it's a strong positive negative attraction, it's going to be a stronger bond. If it's a weaker positive negative attraction, it's going to be a weaker bond. And the positive negative attraction is going to kind of depend on the type of molecule. And by that I mean whether it's polar or nonpolar. It's going to make a big difference as to how strong that force actually is. These intermolecular forces, like I kind of hinted at here a second ago, actually determine what state of matter things are, like naturally. And we're going to look more at that here at the end when we talk more about what these are. Okay, so there are three basic types of intermolecular forces, and we're going to start out with actually what is the weakest force, and it's called a dispersion. So it's a dispersion force. They are also called London dispersion forces, but we tend to just call them dispersion forces. Okay, a dispersion force is between two nonpolar molecules. That's the important part there. Well, if something is nonpolar, that means you don't have a positive or negative end to the atom. Or molecule, sorry. No set positive or negative end to the molecule. So even though the bonds themselves might be polar, these molecules are not. So overall, this molecule has a positive end, or doesn't have a positive end, doesn't have a negative end. All right. Well, they still do stick together. Okay. Something like hexane or octane. Okay. If you have gasoline, there's a whole bunch of that. It all sticks together. It's a liquid. All right. So something has to stick all that together to make that liquid. Well, what all sticks together is a small positive negative attraction. All right. And that small positive negative attraction is actually due to your electrons. All right. And it's due to your electrons based on how they move around each atom or the molecule. Okay, because what can happen is as all these electrons move around the outside of your atom or outside of your molecule, okay, they don't all move the same, they don't all end up in the same spot. So if I have two, say, oxygen molecules, so I have an oxygen molecule, another oxygen molecule, all right, they have to somehow try and stick together, all right, and that intermolecular force is that force between the two there. So something that's keeping that left O here stuck to that right O. Well, the only way they're going to stick together is if one end is a little positive and one end is a little negative. Well, how does that happen? Well, it happens because you have electrons that are outside the atoms, okay? And electrons have their own little charge, all right? And as they move, say with this one on the left, my electrons end up moving and I end up with more electrons on the left than I do on the right. So this side is going to be a little negative, that side's going to be a little positive. Maybe it comes across on another molecule where the opposite has happened, where these electrons kind of are all overloading this side, and that side's a little more negative and this side's a little more positive. Well, if they come into contact with one another, they're going to stick. All right? So it's all about your partial kind of charges with how these electrons travel. So we'll have a partial charge, either being negative or positive, as soon as the electrons move. But if they move again, as they move again, it's going to actually then undo that partial positive or negative. So now let's say we come back to this one and now my electrons have moved and now I've got more negatives on the right side. Well, if I got more negatives, so this is going to be negative, that's going to be positive. Well, now negative and negative don't work, so that's going to break. So as soon as they move again, so as soon as your electrons move again, the force tends to break. Which is why these are very, very weak forces. Okay, you very easily smell gasoline, which means that the liquid form of that very easily becomes a gas because the liquid and the liquid will separate apart, they break apart, and you've got these gas molecules. And the only way you smell something is through the gas form. So things that you tend to smell usually have a dispersion force and are usually very small intermolecular forces. And I'll recap that when we get to the bottom of the page. Okay, so now on to type 2, which is the dipole-dipole forces. Okay, a dipole-dipole is now between two polar molecules. This one's a little bit easier because since it's a polar, that means you have a positive and negative end to the molecule. So you have a set positive or negative end, okay, to the molecule, and that is based on electronegativity. Where your more electronegative one, it's going to be negative. All right. Since this is not a temporary force, that means that it's a lot stronger. Because the one that is more electronegative is always going to be the negative one. The one that's least is always going to be the positive one. So, for example, if we have HCl trying to be attracted to another HCl. Okay, notice how I never have the same atoms attracting because that wouldn't make sense because the chlorine is more electronegative, so you usually see the little S thing there. I tend to just do the symbol or just do the negative, okay? And this one's negative here. H is positive, H is a positive because it's less electronegative. So this positive and the negative there are going to attract and stick together. If a negative would come in contact with a negative, they just aren't going to stick. But this is much harder to break here in the middle just because it is, again, a positive and negative that's not going to change all of a sudden. This chlorine is not all of a sudden going to become positive. Okay, the last one, and actually a very important one that you will see all the time, deals with water. Okay, this is between an H atom of 1, which is why it's called hydrogen bonding, and an N, an O, or an F of another atom or another molecule. And the reason it has to be that, okay, is because the NO and the F right here are your most electronegative elements. So what that means, okay, is that makes a very skewed molecule in terms of charge. So it makes your charge distribution very uneven. Because what's going to happen is your H is going to be really very unelectronegative, which means that he doesn't want electrons around him at all, okay? And since he's only one positive and one negative, if he loses his negative to somebody else or kind of doesn't want it as much anymore, he really only is a one positive that's left. So when your negative is gone, you're left with a 1 plus charge. So a hydrogen bond is almost bond strength, like an actual covalent bond strength. They're very, very strong. And again, it's just really due to the fact that your positive and negative are very, very uneven. Again, because your NO or your F really pull on your electrons a whole lot. All right, so for example, I could have an HF, okay, and he's going to want to bond with another HF. The F's going to be negative, the H is going to be positive, H is going to be positive, F's going to be negative. That hydrogen bond right there is really, really hard to break, and it's very, very strong. Again, because it's very, very skewed. So when you see things like the little water skimmers, okay, that run across ponds, okay, that's due to what's called surface tension. And surface tension is due to hydrogen bonding. So the hydrogen bonds actually can bend because they're actually so strong that whatever this water skimmer weighs is not nearly as much as what that bond has to break it. Okay, it has to do with how hydrogen bonds form. Okay, so I have a little water molecules here. They're purple with the two yellows. Notice how purple is always by another yellow. All right, and so they all kind of stick together like that, and they kind of create these big, actually, gaps or holes in there, which is part of the reason why ice floats, because ice actually has little pockets of kind of air or open space everywhere throughout it because of how these hydrogen bonds actually go together. So since we deal a lot with water, we deal a lot with hydrogen bonds in terms of things that deal with ponds and the little animals, or just why water takes on a kind of a curved shape a lot of times, or a spherical shape when it's being dropped. Okay, and we'll look a little more at that in your lab. Okay, but again, we're between two molecules here. Okay, the last part, all right, kind of a recap. Okay, forces and properties is if you have a weak intermolecular force, all right, that's going to be a low melting point or boiling point. All right, which means that the molecules are easy to break apart or stretch, depending on if you're just going to melt them. Which, like I mentioned earlier, also means that they vaporize easily, which usually means they're going to smell. Not all, but a lot. Okay, the opposite then is for your large intermolecular forces. Okay, if we tie that to states of matter, a large intermolecular force is going to tend to usually be in a solid state because that force is going to keep it together. So the force holding the little molecules together is going to be really large compared to your kinetic energy. So for example, and this is the last thing. For example, okay, water is a liquid, but chlorine, Cl2, chlorine, is a gas, all right? But they're both at room temp. So what makes one a solid and the other a gas? Well, water has much stronger forces that keep it together to keep it as a liquid. Chlorines are very weak nonpolar forces, so it's a dispersion which makes them easily break and become a gas.